Hello, everyone. Miss Lynn Sison. I am coming to you with just a little introduction and a little review to total mechanical energy. So, we're going to look at those transformations, those changes between potential and kinetic energy. As we've talked about, there are two types of energy that we're looking at: the kinetic energy and the potential energy. Kinetic energy is the energy of motion, and potential energy is stored energy. So there's lots of different kinds of potential energy. We are primarily going to look at gravitational potential energy, but there's also elastic potential energy. So gravitational potential energy depends on the position of the object. So that's the height. And then elastic potential energy is stored anything that's elastic, and it's stored by either stretching the elastic object or compressing it. So what we have been looking at and what we're going to continue to look at is gravitational potential energy. So this is a formula. It's the mass of the object time gravity, which we're always going to use this 9.8 meters per second squared, or meters per second, times height. So that's the formula we're going to be using for gravitational potential energy. So I'm just going to do a couple of examples just to sort of remind you. I think that there are some people, sorry, that are still a little bit not 100% on this. So I just want to do a couple for you. So gravitational potential energy is mass times gravity times height. So the mass of this object is 5 kilograms. The height is 13 meters above the ground. We typically think of it as above sea level. And gravity, of course, is going to be 9.8. So I'm just going to, as the formula says, I'm just going to multiply these three numbers together, which is going to give me gravitational potential energy of 637, and we're going to use joules for the unit. So this is my answer: 637 joules. All right, and we're going to look at one more. In this example, we know one of the variables, we know the gravitational potential energy, and one of the variables, and we're going to solve for the other variables. So we always know that gravity is 9.8. In this case, Sam has a mass of 39 kilograms, and he has 300, or they have 328 joules of gravitational potential energy. So I'm solving for height. So height, if you rearrange this, is going to be your gravitational potential energy divided by your mass times gravity. So your mass times gravity, 39 times 9.8, woo, easy for me to say. These two things multiplied together is 382.2. So I'm going to take my 328, which is my gravitational potential energy, and I'm going to divide it by 382.2, which gives me a height of 0.5. Sorry, that's not what it says. 0.8 9 meters above sea level, so above the surface. So that's how you solve, and you can solve for mass exactly the same way by dividing gravitational potential energy by your height times your gravity in that case. Woo. And of course, the other variable, I mean, I'm sorry, the other type of energy we looked at was kinetic energy. So, kinetic energy is the energy that you have from motion. So, it's always going to have velocity. And that velocity is squared, which, if you remember, squared just means times two. So, the velocity has a bigger impact on kinetic energy than mass does. So I'm just going to do a couple of these real quick. So determine the kinetic energy of a 600 kilogram roller coaster that is moving at 18.3 meters per second. So it's one half the mass of the object times velocity squared. So I put it in like this. Your mass is 625 kilograms and your velocity is 18.3. And remember, you want to square that. On these problems, be real careful how you're putting this in your calculator. It's so easy to put it in wrong, and then, of course, you get the wrong answer. So if I multiply one half times my mass times my velocity squared, I get 104,653.13 joules of kinetic energy. All right, I'm going to skip a little bit. Okay, this is really the meat. That was just a quick review. This is really the meat, the most important part that I wanted to talk to you today about is how are potential and kinetic energy related, or vice versa. So, energy can be transferred from kinetic to potential, from potential to kinetic. However, like we have talked about so many times, uh, I just spell that wrong. Conservation, not conversion. It's conservation of energy. And this works exactly the same way that all the other conservation things that you study in science do. There's energy is not created or destroyed. It's just rearranged from one to the other. So like on a roller coaster, when it's up high, primarily potential on the ground, primarily kinetic. And what happens is as the height lowers, the velocity increases. So the total energy stays the same, it's just converted from one to the other. So in this scenario, um, the the really it's really an easy thing to do. This is total mechanical energy. That T stands for total. And it's always going to be preserved. It's either going to be kinetic or potential. Sometimes, like when it's standing still at the top of a hill, it's all potential. When it's rolling on a flat surface, all kinetic. And at all the points in between, it's some potential, some kinetic, based on the height and the velocity of the object. All right. So we're going to look at a real simple example here. We're going to look at a skateboarder that's going up a ramp. So at the bottom, we're going to assume that this skateboarder's height is 0. So he has a height, or the person has a height of 0 meters. All right. So what that means, if the height is 0 meters at the bottom, this person has a gravitational potential energy of 0. Okay. So no potential energy. So we're going to put that right here. What they do have is kinetic energy. So we're going to multiply 0.5 times 60 times 8 meters per second squared. So 0.5 times 60 times 8 squared gives me a kinetic energy of 1920. So my formula is total mechanical energy equals kinetic energy plus potential energy. So I'm going to add these two together, which is really easy because it's super easy to add something with a 0. So this skateboarder has a total mechanical energy of 1920 joules. So at every point, when it's going up, when they come back down, their total mechanical energy is going to be 1920 joules. All right. So I'm going to clear this one, and I'm going to go on to the next one. All right. So in this case, where this person is down here, I'm going to go ahead and put my numbers back in here. And watch this little bit of magic. So here, the person still has 1920, a total of 1920 mechanical energy. But now, since this person is 1 meter above the ground, they're going to have some gravitational potential energy. So I have to calculate that first. So I'm going to say my mass, which is still going to be 60, still going to be, I'm going to write it all out. It's still going to be 60. And I know that gravity is going to be 9.8. And this person is moving at 1 meter per second. So essentially, I'm just going to multiply 60 times 9.8. All right. So I know that this person has gravitational potential energy of 588 joules. And I know that they have total mechanical energy of 1920 joules, which means they've got to have kinetic energy of 1332 joules, because total mechanical energy is going to be my potential plus my kinetic plus potential. Is addition, doesn't make any difference. Okay, so I just did the math on that. All right, now let me show you how you can figure out how fast this person is going. This is the one thing we really haven't done yet. So if I want to figure out velocity, my velocity is going to be equal to my kinetic energy divided by 0.5 times the mass. All right, that's the formula for it. So I'm going to put my numbers in there. My kinetic energy is 588 joules, and 0.5 times 60. So I'm going to take 588 divided by 30. But wait, that actually gives me my velocity squared, which is 19.6 19.6 meters per second. But I don't want my velocity squared. I just want my velocity. So the final step in this operation is going to be to square root this number right here, which gives you a final a velocity of this person right at this point of 4.4 meters per second. All right, give you a second. Might not be a bad idea to take a picture of this. Might be helpful to you later. All right. Now, let's put it all together. Okay, 1920. Oh, whoa. 0, 1920, 1332, 558, 1920, 4.4. Okay. All right. So now this person still has 1920 joules of potential energy. Something that's missing here. We're going to say that this person is now, sorry, at a, I'm going to get this, at a height of 3 meters. All right. So I'm going to do this same thing again. I want to figure out the velocity. So the first thing I have to do is do my gravitational potential energy, which is my mass times my gravity times height. So my mass is still going to be 60 times 9.8 times 3. So I'm going to say 60 times 9.8 times 3 gives me a gravitational potential energy of 1764 joules. And you would expect that at this point, there would be a lot of potential energy because this person is at a height that's 3 times higher than before. All right, which, whoa, ah, sorry, it's so tiny. Which gives me a kinetic energy of 156 joules. That's my kinetic energy. My height is 3. So now to figure out my velocity, I'm going to take my kinetic energy divided by 1/2 times my mass, which is 60. So I'll just put my kinetic energy in here. So I have 156 divided by 30, which gives me a velocity squared actually of 5.2, but I don't want velocity squared. I want velocity, so I'm going to have to do the square root of that. So my whoa. Hope if I put it in the calculator correctly. So as one would expect, at this final spot, this person that's 0.73, this person is not moving very fast because most of the energy is in the potential energy. So the person is not moving very fast at all. So this is how you calculate conservation of energy. It looks like a lot, but I think once you see the pattern, you will recognize that it really is not that difficult. So typically, we're going to have a scenario where you start off either the person, the object, the whatever it is, starts off on the ground or starts off at the highest point. You calculate whatever energy is appropriate and you just move forward. All right. So that is conservation of energy. Thank you for watching.